Okie dokie, so today is just all going to be, number one, about delta G calculations. And number two, it's going to be about looking at KEQ from an AP perspective, just adding a few little extra things in. Okay, so delta G, these are the three formulas that you are given on your data sheet. This is page 105 in the blue book. So if we go to our data booklet, we can look and we can say, aha, here's delta G. And in fact, we have 4 equations. The very last one, though, we won't get to until the electrochemistry unit. That's going to be our last unit, that one there. So really right now, we're only dealing with these 3 here and not that one. Okay? There we are. So we're going to whip through some of these fairly quickly because it's really just throw them in the right formula and then churn through the numbers. Okay. So if you were asked to calculate delta G at 290 K for the following reaction, and you are given this reaction, there you are. And if you are given delta H and delta S, which of those 3 formulas would you choose? First one, yes, because you got your delta H and your delta S. Really, the only reason that I've got this example in here is because it gives us a chance to remember that whenever we're dealing with entropy, the units become important because entropy is given in joules and enthalpy and Gibbs free energy are usually in kilojoules. So you have to make sure you make those agree before you do anything. And the other thing is that you also have to be careful that your temperature is in Kelvin. Okay, so if you're given a temperature in degrees Celsius, you need to make sure it's in Kelvin, and you need to make sure that everything's in joules or everything's in kilojoules, one or the other. So basically, we just say, okay, I'm going to take my delta S and convert it into kilojoules. So my joules cancel out, and you get that, and then you just plug everything in. Delta G is equal to delta H minus temperature in Kelvin, delta S. The Kelvin cancel out, and you are left with kilojoules and kilojoules, and so you get 77 kilojoules. Now, sometimes you'll be given kilojoules per mole. Sometimes you'll just be given kilojoules. Just go with whatever you are given. Does that make sense? Okay. All right. Now we are told that this is negative 77 kilojoules. That is our delta G. What does that tell us about this reaction? It is doesn't necessarily tell us it's exothermic. Delta H negative would tell us it's exothermic. Delta G tells us it is spontaneous. And in AP language, it tells us that it is thermodynamically favorable. Yes. Okay, excellent. All right, example number 2. We have the formation of ammonia. And this time, we still want delta G naught. And this time we are given delta G knots of formation. That's what those little F's stand for. F stands for formation of all the substances. Do you guys know how to do this one? Which formula would we choose? We would choose formula number 2. Okay? And once again, we're not going to spend too much time on it. Just remember that you need to make sure that your coefficients do the multiplying when they need to. Okay, and always make sure products go first, reactants go second. I have a tendency to put them in the wrong place. At any rate, we end up with negative 32.90 kilojoules per mole. What does that tell us about this reaction? This reaction is thermodynamically favorable. What would this tell us about our value of KEQ? KEQ would be greater than 1. Yeah, if you have a negative delta G, then KEQ is greater than 1. Alrighty. All right, this next one, we have information here. This is a big, bad, long question, okay? We want to find out if NH4NO3 will dissolve in water, so that is ammonium nitrate. Will it dissolve in water at room temperature, 25 degrees Celsius? We're given values for delta H naught, and that would be in kilojoules per mole. We're given values for delta S naught, which is in joules per mole. Per mole what? Kelvin. Okay. In order to do this, what do we need to know? Or what do we need to think about or write? In order to do any of these things, you're going to need some sort of reaction, yes? What will the reaction be here? It's easier than you think. It's going to be the dissociation of NH4NO3. Okay, so we're going to write the dissociation of NH4NO3. There we go. All right, so now we have our reactants, we have our products. And wouldn't it be nice if we could just add up our delta G's like we did last time, products minus reactants? But we're not given delta G's. What are we given? We're given delta H's and delta S's. Okay. So what are we going to have to do first? Yeah, we're going to have to take all of these and find delta H naught of the reaction. We're going to have to take all of these and find delta S naught of reaction. Yes. Standard state. Yeah. It depends on where you put it. If you put it at the bottom, it can mean initial. If you put it at the top, it means standard state. Yeah. So, how do you remember the formula to find these ones? How would you find the delta H of reaction from all of those delta H naught Fs? Yeah.
The first one is positive.
Yeah.
Positive, and the negative.
Yeah. So what you would do is you would just use the sum of delta H naught reaction. Sorry. Is the sum of delta H naught of formation of the products minus the sum of delta H naught F of the reactants. Okay, so you would do all of that, just like we did for the previous question for delta G. How would you find delta S naught? Same thing, but for delta S. Okay, and so we actually have that here, so we don't have to worry about it too much. Okay, so we've got, here's our products. For delta H, here's our reactant for delta H. Okay, with our coefficients there, it's all 1 to 1 to 1. We add it all up and we get 28.05 kilojoules. Now, I probably wouldn't have bothered putting the mole here and canceling with the mole. I probably would have just left it in kilojoules per mole and just chucked the coefficients in front. Either way is okay. If you do it without the mole here, you'll end up with kilojoules per mole. Does that make sense? Either way is fine. Okay? Yeah. You won't be given a table like this. That's a boo-boo on my part. I need to fix this. Because you should be given the units. Yeah. All right. So now we have our kilojoules. Now we calculate delta S. So we've got our S of our product. Okay, so here's our product. And then we've got S of our reactant. Just the one reactant. And we add those all up and we get joules per Kelvin. So this here is our delta H. This here is our delta S. And those are both of the reaction. So those are our all overall. And once you have those, what are you going to do with them to find delta G? We're going to throw them in equation number 2 and do the little multiply by t and subtract, okay? But before we do that, before calculating delta G, ensure that your units are compatible. So temperature has to be in Kelvin. If you do not remember, 273.15 is what you need to add. Where could you find that? You could find that in your data booklet in the gas section. I think gases are here. Probably. Yep. Okay, so they give you the temperature that is 0 degrees. Okay, so if you forget that number, it's there for you. 273.15. All right, so now we've got it in Kelvin, and we look at our units for delta S, and this is in joules, and our delta H is in kilojoules. I would have a tendency to put everything into kilojoules because usually delta G is in kilojoules, but if you put it in joules, there's nothing wrong with that. Okay, so here I've put delta S into kilojoules, and I don't know why this is down here. This should really be up here. Okay, that's delta S, not of the reaction. I need to fix this, also fix. Yep. And there's our delta H. And then we toss them all into our delta G on our next page. Whew. Okay, so we got our correct temperature, correct, everything's correct. And we get delta G is negative 4.4 kilojoules. What does that tell us about the solubility of ammonium nitrate? Because remember, this was our NH4, NO3, NH4 plus, NO3 minus. Does it dissolve? Yes, because it's got a negative value, so it is spontaneous. Now, did you need to calculate delta G to find that? No, because do you know your solubility rules? What do you know about ammonium salts? NH4 plus salts are always soluble. The other one that's always soluble is nitrate. Oh, guess what? You have ammonium and nitrate. So it's always soluble with always soluble. So it is soluble. What is the other one that you should know that are always soluble? It's actually a group. Oh, I heard it somewhere. Alkali, the alkali ions. Okay, so the alkali ions, ammonium and nitrate are the ones that are always soluble. Yes. The first. Yeah, just the first. Alkali, but not alkaline earth, which is the second row. Column, not row. Okay. And those are the only 3 solubility rules you need to know. You should be thankful when I started teaching this, you had to memorize all the different solubility rules. Back in the day, there was a lot more memorization. They've gotten rid of it now. You used to have to know colors of ions and stuff. It was weird. Anyway. All right. Example number 4, we have another solubility thing. In this case, we've got lead iodide, PbI2. And we are told that it has a solubility product constant, which is called the KSP. Anyone want to guess what a KSP is? It's a solubility product constant, but it's basically just a KEQ for a solubility equilibrium. Okay? KSP, and this is going to be unit 3, which we're going to do after unit 4. Okay, KSP is the KEQ for a solubility equilibrium. And we are told that it is 1.4 times 10 to the 8. And we are told that that is true at 25 degrees Celsius. Calculate delta G to determine if lead iodide is appreciably soluble. So which of our 3 formulas would we use to calculate delta G? We would use number 3. We've got negative delta G, delta G is equal to negative RT ln K. Now R, sadly, if you're in the thermodynamics section and you look up R, it just tells you that it is the gas constant. Okay, so you're over here and you're like, gosh, wouldn't it be nice if they told me the value of R because it's right here? But no, you would have to flip to the page before in gases. Yeah. And you'll actually find the values for R. And there are 2 of them given. I think when I wrote this worksheet, there were 3 of them given, but now there's only 2 given. And one of them has units which have joules. And the other one has liter atmospheres. We are doing a calculation to find Gibbs free energy. Which R value do you think we will use? We're going to use the one with joules because we're finding Gibbs free energy. Okay, and energy is measured in joules. So if you're doing things with volume and pressure, use the second one. If you're doing things with joules, use the first one. Okay. So there's a lot of just fussing around with different units here, okay? So here is our negative. Delta G naught is equal to negative RT ln K. And which value for R should we use? We're not even given this one anymore, so I'm going to get rid of this. Okay, we're going to fix that. We're going to use this one because we're dealing with Gibbs free energy, therefore joules. Okay. What do we need to do with temperature before we plug it in? Kelvin. Okay, so now we've got plus 225 plus 273.15 is 298.15. If you take any chemistry at university, you'll probably know that number by heart by the time you are done, because we do things at 25 degrees Celsius a lot. And so we just throw everything in there. There's our R value, there's our temperature, there is our K, and let's see what happens with our units. We have Kelvin cancels with Kelvin to the -1. And the natural log of KEQ has no unit, so we are left with joules per mole. And probably because it's delta G, we would probably like it to be in kilojoules. So let's translate that to kilojoules. What does this value of delta G tell us about the reaction? It's non-spontaneous. It is thermodynamically unfavorable. What does that tell us about the solubility of lead iodide? It is not very soluble. It will dissolve a teeny tiny bit, but it's really teeny, really tiny. Okay, so the forward reaction is not favored. So it is mainly insoluble. And in Unit 3, we will spend most of our time looking at substances that are mainly insoluble. We'll look at things with like teeny tiny KSPs, okay, and figure out what the concentrations are. And they're all going to be like times 10 to the -3, times 10 to the -5, times 10 to the -7. You know, your concentrations will be teeny tiny. Okay, do we get into any exciting questions yet? Not quite yet. That's okay. We're going to keep going. Here we have the formation of nitrogen monoxide. Oh, and by the way, back here, did we actually need to calculate delta G to see that it was not very soluble? Or could we just look at our KEQ, which is now called KSP, and say, hey, 1.4 times 10 to the -8, that favors the reactants a lot, yes? And so we could say it's not very soluble just based on that. But if the question says, show me using your knowledge of delta G, then you would show them using their knowledge of delta G. Okay. Yes? It's not very small. It is small. It's, yeah. I mean, it is very small. It's just not very small. Yeah. Okay. So we know delta G and we want to find K in this case because we are given delta G, which is 3.4 kilojoules per mole. And it is quite difficult to find the concentrations of each gas because they're in a container together and they're all mixed, right? So if we know the delta G, we can find KEQ. So for that, again, we want delta G naught is equal to RT ln K. And we are told that this is at 25 degrees Celsius. Once again, which value of R should we use? I need to get rid of that. The one with the joules. What should we do to temperature before we check it in the equation? Make it Kelvin. Okay, I know I'm being repetitive, but the more you get it hammered into you, the more likely you are to do it when under pressure. What do we have to do with delta G before plugging it into the equation? Let's look at our R value. We need to make the kilojoules into joules because we've got kilojoules here, and we have joules here. So we need to make those consistent. You could go either way. You could change the joules into kilojoules, or you could change the kilojoules into joules. This seems to have like a very complicated unit, so I chose to convert delta G into joules. I thought that sounded easier. I think I did anyway. Did I? Yes, I did. Okay, there we go. So there's our delta G. Now it is in joules, so it is consistent with our R value, which is also in joules. So we got joules and joules. You know those chief readers reports, the things that the readers are always like, you know, after they read the free response questions and they mark them and they're like, what could the teachers do to ensure that students perform better on this section? And a lot of this stuff comes down to making sure your units all are the right ones and that they are all consistent. Okay, so there's a reason I keep harping on it. Okay, so we would need to take this, and I would personally, before throwing everything in and having to move around all these numbers, I would probably just solve for ln K first. So ln K is equal to delta G over negative RT. And then you can chuck in your numbers. Okay, so there's our delta G, there is our R, there is our T. We get our answer. It is negative 69.95, and that is the natural log of K. Do you guys remember how to unnatural log something? Yeah, you use the shift button, okay, which ends up being the E to the X button, okay? So you would just use your E to the X button, and you would check with your sig figs. Where are my sig figs here? Why did I go to 2 sig figs? That's a question. Huh? This would be 3 sig figs. This is 4 sig figs. That's 4 sig figs. I don't know why I went to 2 sig figs. That sounds wrong. Let's change that to 3 sig figs. Okay, so we got 69.953 negative. And then I want to E to the X. E to the X. There we go. 4.17 times 10 to the negative 31. Why is it not 4 sig figs? Because we were told that the temperature was 25 degrees Celsius. And what that means is when we add 25, the 5 is the uncertain digit. So that means when we add it up, there's my uncertain digit there. This is my uncertain digit here. So my ones position is uncertain. So I cannot go past a single uncertain digit. So that has 3 sig figs. It's always that addition and subtraction that gets us. Yes?
If the form of the reactions at standard state, would that be an input sequence? Would that?
I think if you're told it's at standard state, you could probably just go with 273.15 or 298.15 and be done with that. Yeah.
So
It would have 5. Yeah. Yeah. Okay. So that I need to fix. Okay. So we have an extremely small K value, which goes along with our large delta G, positive delta G. Okay. What was our delta G? Our delta G was times 10 to the 5, so that's pretty darn big. And then our K is very, very small. So the reactants are highly favored. Hardly any product gets made. Are we good? The clock's wrong, by the way. It's running slow, if you're wondering. It's almost 5 minutes slow now. I think I need to throw a new battery in there, maybe. Yeah. It used to be 2 minutes slow about a week ago, and so I'm like, okay, maybe we need a new battery. Oh, example 6. We finally get to something exciting. Do you remember how to do Hess's law? That is a resounding silence. So it's a good thing we are doing this. Okay, I'm just going to grab this. Okay. The nice thing is that Hess's law is really just about playing with equations so that they end up equaling the overall equation. So it makes it very similar to reaction mechanisms where you need to get everything to add up to equal the overall. Okay? These are not mechanisms. They are just reactions. And if you recall, delta G is a state function. So if we can make reactions 1, 2, and 3, for which we know the delta G's, add up to give us the overall reaction, then the delta G for the overall reaction will equal the sum of these. But we have to play around with these a little bit to get it to equal. Okay? So how do we go about this? Well, what we're going to do is we're going to say, I want these 3 things to add up to give me this. How do I make these add up to this? Because right now, if we were to add them up, we would not get the reaction at the top. Yeah? We just wouldn't. But we can do things. We can say, what do I need in my reaction? I need some NO2, right? As a reactant. Do any of these reactions give me NO2 as a reactant? Oh, look! Oh, yay! Okay, that's good. But there's still a little problem with it. What's the problem with it? There's 2 of them. So what would I have to do to this reaction before I could use it? I'm going to half it, okay? And yes, you could say divide by 2. I'm going to say multiply by a half, and you'll find out why later, okay? Just because it comes in handy later when you're doing stuff with KEQ, okay? Doesn't matter. If you want to divide it by 2, that's fine. But I'm going to multiply by a half. Oops. And if we multiply the equation by 1/2, what are we going to do to its delta G? We're going to multiply by half, okay? All right. Is there anything else from that top reaction that we can see? Like NO2, do we have some NO2? Yeah, we have NO2 on the first one. Okay, so we got some NO2 on that first one. NO2, here we are. And we got some NO2 here. Now with this one, we have two problems. First problem is, what's our first problem? Yeah, we have too many and it's the wrong way. Okay, so there's too many and it's the wrong way. So we need to both flip this. Okay, so it's going to be backwards. And we need to multiply it by a half. What is going to happen to delta G if we flip the reaction and multiply by a half? We need to change it to positive. Okay, so we need to change it. I'm going to say we're going to multiply by negative a half, and this negative is changing the sign. But feel free to just stick a positive in front of it too, right? Like if you were there, you could just be like positive times a half. That would also be totally fine. Okay. Now, where do we see NO in this equation or in these equations? We see it in the second one. And we also see it in the first one. So we got some NO here and we've got some NO here. So my first instinct would just be to say, okay, you know what I'm going to do? I'm going to add up. I'm going to put numbers 1 and 3 down. This is not actually a mechanism, so it doesn't matter what order I do things in. So I'm going to write down reaction 1. And I'm going to flip it and multiply by a half. So I'm going to have NO2 goes to NO plus O2. So that's reaction number 1, but we have flipped it and we have multiplied by a half, except for I forgot to put the half in front of the O2. There we go. And my delta G then is going to be 71.2 divided by 2 is positive 35.6 kilojoules. Reaction number 3 is the other one that I know for sure what I'm doing with it. And I'm just multiplying by a half, so we end up with N2O goes to N2 plus 1/2 O2. And we get negative 103.7 kilojoules. Now we want this whole thing. I'm gonna have reaction 2 in here as well. We want this whole thing to add up to N2O plus NO2 goes to 3NO. So reaction number 2, I'm assuming it's probably going to be, let's take a look at what we've got. We've got N2O, that's good. We got NO2, that's good. And we have one of our NOs. We need 2 more NOs, right? And aren't we lucky? What does reaction 2 give us on the right? It gives us 2 NOs. Oh, yay! Okay, so that takes care of our 3 NOs there. And then let's just put the front part of that on there. So we've got N2 plus O2 N2 plus O2. And by golly, everything that needs to cancel out, because 1 O2 needs to cancel out, right, to get the overall. So that's going to cancel with that. And an N2 needs to cancel out with an N2. So that's perfect. And so reaction 2 can just stay the way it was. So its delta G doesn't change at all. And that's equal to positive 175.2 kilojoules. And then we just add all of those up. So that is a thermodynamically unfavorable reaction, yes? Yes, I did, and I need to fix that. Thank you. Now, in the workbook, you'll notice I did it differently, right? Like I didn't do it the same way. I think I did reaction 2 and then 3 and then 1 and I don't know. Anyway, it doesn't really matter. What you just have to do is you have to be like, it's not going to be too complicated. I'm going to be multiplying things by at most 3 or a third or something like that. You know what I mean? It's usually going to be like either multiplying by 2 or dividing by 2. Or you'll have to flip it, or you might have to do both of those. Yes? Hess's law can be used for any state function. Yes. And I think entropy is not a state function, so you can't do it for that, I think. Is entropy a state function? Let's find out. And if it's not, I don't understand why it's not, but that's okay. Is entropy a state function? Yes, it is. Excellent. Okay, so they're all 3 of them state functions. That actually makes more sense to me. I don't know why I thought it wasn't. Anyway. Yes? Okay, very cool. All right, so you would do the same thing if you were given a delta H and you were given the delta H's of various reactions. It works out all the same. Okay, here's kind of a weird one. Example 7 on page 110. Calculate the temperature in Kelvin at which the sign of delta G changes from positive to negative. Assume that delta H and delta S naught are constant and do not change with temperature. Goodness. So we want to find a temperature, and we've got a delta G, and we got a delta H, and we got a delta S. What formula do you think we'll be using? The first one. Delta G equals delta H minus T delta S. And let's stick our knots on there because they're all knots. Now, delta G is changing from positive to negative. What does that tell us about delta G? What do we know about delta G when it changes from positive to negative? It is 0. Okay, so when delta G changes from positive to negative, that means that delta G is 0. So we are simply going to take this equation and throw in everything. Okay, so I'm going to take delta G is equal to 0. And delta H is equal to 41.2 kilojoules. Let's get rid of the per mole here because otherwise it doesn't work consistently. Fix. Okay. And then we're going to add T delta S So are we happy with what I've got there? Not happy? What do I need to do? Change the joules. And you know what's really nice is you can just put times 10 to the negative 3, and that changes it to kilojoules. And it really doesn't matter that it's not in scientific notation because you're not giving this as your final answer. Yeah? All right, so now we can deal with this. In fact, I probably would have preferred, if I was doing this, to have 0 is equal to delta H minus T delta S. I probably would have solved for T first, right? And then thrown my numbers in, but it doesn't really matter, okay? If I did solve for T first, I would end up with negative delta H is equal to negative T delta S, and those both become positive. And if I want T by itself, I'm going to divide by delta S, which gets rid of the delta S over there. So T is equal to delta H over delta S. So that's going to be, that was delta H, 41.2 kilojoules divided by 42.1 times 10 to the negative 3 kilojoules. And we get 978.6 3 sig figs. And that becomes, kilojoules per Kelvin. Because otherwise, we don't have a right unit. So we've got 1 over Kelvin. So that's going to be then Kelvin. And that should be 3 sig figs. So that should be 979 Kelvin. So below (979 Kelvin), we are unfavored. And above 979 Kelvin, it's favored. Yeah. Is good. Okay. Let's see if that's it. Yes, it is. So we are now done with Gibbs and entropy. So you're going to have some questions from that for homework tonight. Right now, we are going to go to section 2.5, which is also in the blue book. And I think this is on page 84. 84. So in AP, you will come across this constant called Kc. C stands for concentration. And it literally is exactly the same as KEQ. Why do they give it another name? To distinguish it from when we use pressures, because in AP you will be given pressures And that one is then called Kp for pressure. Okay, so Kc is just Keq. You'll notice the expression is identical. Kc, same thing. Okay, it is your products over your reactants. So that is it. Kc, just like Keq, but because it is Keq, is independent of concentrations, it only changes with temperature. That's just a way of saying Keq, Kc, which is Keq, only changes with temperature. Nothing new. We already knew that. So in AP, we will have partial pressures, which we will use Kp for. Now, I think I talked about this a week ago or so, that you can relate rate law to Keq. So we're going to look at that right now and see how they relate. But it's easy. It's actually easy math. So let's consider the following elementary reaction. What that means is that the forwards reaction is an elementary process. And the reverse reaction is an elementary process. What is special about elementary processes when we are writing rate law? Yes? The coefficients are the exponents. So look at this. We've got a 2 here, and our forward rate, okay, we've got rate is equal to K times HI squared, and we're going to call it Kf because it is the forward reaction. So that is going to be our rate constant for the forward reaction, Kf. Our reverse rate, we're going to call the rate constant Kr, R for reverse, and we have no coefficients, so we've just got H2 and I2. Now, this is an equilibrium. What do we know about equilibrium? What is true? Forward rate equals reverse rate. So, oh, look at that. Those two are now equal. So that means we're going to take this, and we're going to put it here. And we're going to take this, and we're going to put it here. And then we're going to combine all our K's on one side, and we're going to combine all our concentrations on the other side. Okay, so I'm going to take my reverse K and I'm going to bring it down to the other side. And I'm going to take my HI squared and I'm going to bring it down to the other side. And guess what? What is this thing here? That's our Keq, yeah? Or Kc. So how does equilibrium constant relate to the forward and reverse rate constant? Well, the Keq is equal to the forward rate constant divided by the reverse rate constant. Super exciting. Now, I do not think this will show up on an AP exam. I don't think they care that you can relate the two. But I hate to say never and then have it be there. And then you'll be like, ah, okay. Now we get into the things that are actually important. And this one here, number 1, is part of the regular curriculum. The only reason I have it in here is because that we are going to learn 3 things, whereas regular chem only learns 2 things, and we're going to combine all the 3 things into one big thing. So I put it in the blue book, even though it really should be part of the pink book, okay? So if anyone wants a sticky note to mark this page, there's some sticky notes right there. Okay. So this is testable. So what happens to Kc or KEQ if we change the direction of the reaction? So we take it from being NO plus O2 gives 2NO2, and we flip it around, we reverse it, so now we have what was the reactants is now the products, and what was the products is now the reactants. So we have reversed the reaction. Well, if we look at our K values, we've got NO2 squared in the forward is on the bottom, and in the reverse one, it's on the top. And our NO2 is on the top for the forward reaction, and it's on the bottom when we reverse it. So what do we call that process where we take something, we would flip it upside down? We are finding the inverse or reciprocal, yes? Is there a difference between inverse and reciprocal? They're the same thing, right? So if you reverse a reaction, the K value is flipped. So what you would do is you would take 1 and you would divide by, like if you were given Kc, let's find a different color pen. You would throw it in there and just put 1 over and you get your new value. Does that make sense? Let's call it Kc reverse. Does that make you happier? Okay. Prime usually just means we have manipulated it in some way. But you can just call it Kc reverse. I kind of like that better. 6. And then you just chuck the number in and you get whatever you get. So, in general, the reverse reaction is going to be 1 over Kc. There you go. All right, so that could be on the regular test. Yes?
So we were doing this calculation, we were writing out our equations. Do you want to do that with case 5 with how to
I don't care. Doesn't really matter.
but we should differentiate it.
Differentiate it in some way. Yeah, okay. Or you could say Kc nu. You know what I mean? Yeah. The other way of writing this, of course, if you wanted to, you could say Kc to the negative 1. That would be the other way of writing it. Totally fine. Okay, now what if we multiply the whole reaction, which means we're multiplying all the coefficients. So if we take this reaction here, what do we have to do to get this next reaction? What's happening? We took the whole thing and we did what? We halved it. So this is where it becomes important to say I'm multiplying by 1/2 rather than dividing by 2. Because what we're going to do is we're going to raise everything to the power of 1/2. Okay? If I were to multiply by 2, I would raise everything to the power of 2. If I multiplied by 7/8, I would raise everything to the power of 7/8. Okay, that's why we're going to go with multiplying, because multiplying lets us do that rule. Okay, and if you divide, then you have to come up with some other rule, and I don't know what it is. Okay, so if we take our reaction and we multiply the coefficients by some number, whoops. Why are you not moving for me? Yes. This is also part of regular, yes. Now, that being said, this is not a common question. So you may not get a question on this. It might not show up on your test. It just depends on which version I happen to give you guys this year. Okay? I think there is for sure one on the review though. So now you know and you can review it. Okay, so here we go. Kc for our first reaction is NO2 squared over NO squared times O2 to the 1. And then if we were to write Kc for this second reaction, we end up multiplying everything by 1/2. So NO2 gets multiplied by 1/2. The 2 gets multiplied by 1/2, and the 1 gets multiplied by 1/2. Instead of doing that, everything's been multiplied by 1/2, all of the coefficients. So we can just raise the entire thing to the power of 1/2. And why would I like to do that? Because what do I know about raising things to the power of 1/2? What operation is that? That's a square root. Okay, and as before, what are the chances of you getting anything more complicated than multiplying by 3 or multiplying by 1/2? Like, not very likely. Okay, you're not going to get like multiply by 6/7. No, that's not going to happen. Okay, you're going to get like, at the worst, you might get a cube root. Okay, where you have to multiply by 1/3. All right. But basically what it comes down to is the rule is that if you multiply the coefficients by some number, n, you raise Kc to the power of n. So what that means is that our new Kc would be equal to our original Kc to the power of n. Yes? Okay. Adding equations together. This is very much like, this particular one actually is a reaction mechanism, but you can do it for things that aren't mechanisms as well. Okay. So here is a possible mechanism for this reaction. And if we know Kc for step 1, and we know Kc for step 2, we can get Kc overall by multiplying the 2. Yes? And we can actually prove this. Shall we prove it? Here is Kc1. Okay, it is NO squared over N2O and O to the 1/2. We have our Kc2, which is NO2 squared over NO squared times O2. And if we look at how those cancel out, if we're adding up the two steps of the reaction, what cancels out if we're adding up the two steps of the reaction? The 2NO cancels out. And look what happens when we multiply these two. The NO squared cancels out with the NO squared. So it's the same thing canceling out as when we're adding the steps. And what we end up with then is NO squared over N2O. And then we've got an O2 to the 1/2. And we've got an O2 to the 1. So that's going to be O2 to the 3/2. There's our thing here. And if we look at this, does this match up with our overall equation? Lo and behold, it does. Okay, so that's why we can do that. So multiplying the two K's for the two steps will give you the overall K. And it does not have to be a mechanism. It could just be random equations that add up to give you an equation. So when equations are added to get a net equation, the equilibrium constants must be multiplied. And let's look at a super fun example where we combine some of these. So exciting. So let's consider these two equilibria here. We have Kc1 and Kc2. And we get a new reaction here. So we've got number 1. We got number 2. And we combine them and we get reaction number 3. And let's now find our new Kc. What do we have to do to reactions 1 and 2 to get reaction 3? Let's see what we need. We need 2 HCl's. Do we have 2 HCl's in reaction 1 or reaction 2? Yes. We need to have reaction 2. This one is just fine, just as it is, right? This one can just stay. But number 2, not only do we have to multiply by 1/2, what else do we need to do? We also need to flip it. What do we do to our, in other words, we're going to reverse it. What do we do to our K value when we reverse? Yeah, reduce Kc reverse is equal to 1 over the forward Kc, the inverse. Yeah? So we're actually going to have to flip this. And then if we are multiplying it by 1/2, what are we going to have to do with it then? We're going to have to raise it to the 1/2. So this one can just stay as it is. So it's just Kc1. Yeah? So it doesn't have to do anything. But now we need to take this whole thing and raise it to the 1/2. And there we go. So we've got that here. We've got that. We've reversed it. Okay, so that's the reverse. This one's halved. So there are actually several ways of writing this now. We need to combine the two. We need to combine Kc1. And we need to multiply it by 1 over KC2 to the half. It would be fine to leave it like that, but you could also write it as KC1 over KC2 to the half. Or you could write it as KC1 times KC2 to the negative a half. Your homework is 88, 87, and 110 to 111, but only do the odd ones, okay? And it's flex time now, right? Yes. Okay. Phew. And very soon you'll be down to one workbook again. Bring the yellow one tomorrow. I think we'll be starting it probably halfway through tomorrow. The pink one you can just leave at home if you want to study with it. The blue one, we need to finish one more thing in the blue one tomorrow. So maybe tomorrow is the day when you just have all of them. Although, yeah, I know. It's the one day, and then we're done. I wouldn't, you don't need the pink one at school tomorrow, right? You can just leave it at home if you're studying from it. Yeah. You're welcome.